All right, this is section 2.3, graph sketching, asymptotes, and rational functions. So we're really just going to be continuing some of the more important concepts when it comes to graph sketching, and these are the asymptotes. Everything that we need for asymptotes is not necessarily included on here, so I'm going to kind of go off a little bit when we get down to the bottom of this particular page and add a couple of things in there. And then on the back page, you'll see that there's actually one additional topic that we're just not even going to cover. It is an algebraic concept. It is important for algebra, but it's not going to be important for what we're doing here in the calculus class. Okay, so our objectives: find limits involving infinity, determine the asymptotes of a function's graph, and graph rational functions. Our vocabulary is rational function, which we have heard before, vertical asymptote, and horizontal asymptote. Okay, all those things are terms that we've probably heard in algebra classes before. So in this section, we're going to add this to the list of features for rational functions specifically. So what's a rational function? A rational function is just a function in which a polynomial is divided by another polynomial. Okay, no root functions, no trigonometric functions, no exponentials, no logs, none of that stuff. It's just got to be a polynomial divided by a polynomial. All right, so let's look at the concept of a vertical asymptote first. This is something that you guys have probably seen before in your algebra classes. A vertical asymptote on the graph at the right there is clearly at x equals -3. You can see the dotted line which indicates that there is a vertical asymptote. And that's the graph, the actual graph there of x minus 2 over x squared plus x minus 6. The reason that this thing has a vertical asymptote is because as you approach the vertical asymptote from the left or from the right, the limit approaches one of the infinities. Specifically, as x approaches -3 from the left-hand side, right here, we're approaching -3 from the left-hand side, you can clearly see that this graph is going to start going all the way down towards -infinity. And as you approach, as you approach x equals -3 from the right-hand side, so we're getting closer and closer to -3 now, the graph itself, the y values, start to go up to positive infinity. The most straightforward way of thinking of this is if one of your sided limits, doesn't matter left or right, or both, approaches an infinity or a negative infinity, you have a vertical asymptote. And that's actually what it says in the definition box below. The line x equals a, which is a vertical line, is a vertical asymptote of f of x if one of the following is true. Either the limit as x approaches a from the positive side goes to infinity, or it goes to negative infinity, or the limit as x approaches a from the negative side goes to infinity or negative infinity. Again, all it has to do is approach either a positive or negative infinity from one side or the other, or both, but just has to be one, and you have a vertical asymptote. So we're going to take a closer look at that, that limit specifically. So the limit as x approaches -3 from the positive side. If you were to plug -3 in there, what you would get is you would get some kind of a whole number value, not whole number, you get some kind of a value on top that's not 0 over 0. So you would get something divided by 0. As long as it's not 0 over 0, we're okay. If you factor it, what you would clearly see is that if I plug -3 into this piece right here, that would give me 0 in the denominator. And once I actually factor it all the way and then simplify by crossing off the x minus 2's, because those will divide out, all I'm left with is 1 over x plus 3. Plugging -3 again into here gives you 0. So what that's really saying is that the numerator stays constant while the denominator is getting really, 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 really small. It can't get to 0 because you can't actually plug -3 in, but it's as it approaches that. So as you take a number and you start to divide it by a really infinitesimally small number, the number on the top that's dividing it basically stays still, so you're going to get an infinitely large number, or it's going to approach an infinitely large number. Let's put it that way. And that's what it's saying. Now, if we look, excuse me, if we look at what we didn't, excuse me, if we look at what we did get rid of, you might ask yourself, well, if I just stop at this step right here, and I say, well, okay, what if I let the limit of x approach 2? That gives me a 0 in the denominator here. Why doesn't that give us an asymptote? Well, again, we haven't simplified this all the way yet. Once we get rid of these x minus 2's, then I don't have that x minus 2 anymore that's going to give me the 0 in the denominator. And when I plug 2 into here, as x approaches 2 now, the denominator approaches 5, so the limit approaches 1/5. So one of the key takeaways there is you must simplify algebraically first. And if you remember, this goes back to previous sections when we were talking about limits. If I plug 2 into the numerator and denominator, we can go all the way back to the beginning here. If we plug 2 into the numerator and denominator, we would get a 0 on top and a 0 on the bottom. Typically, if you get a 0 on the top and a 0 on the bottom, that means that you have a limit. Algebraically, you have to simplify it first to be able to find that limit. Usually, what that indicates is there's a hole in the graph. Okay, not always, but most of the time. In irrational functions, just about all the time, that's what it's going to be. Okay, so that is the concept of the vertical asymptote. Now the horizontal asymptote, which is just a little bit different. Again, this is where a couple of things are going to come into play that aren't shown here. A horizontal asymptote is referring to end behavior. What does my graph do as it approaches x equals infinity and x equals negative infinity, or not equals, but as x approaches positive and negative infinity? In other words, what's happening at the extremes to the left and the right of the graph? Let's go back up and look at this sketch real quick. What is happening as the graph goes way off this way and way off this way? What is the value approaching? What's the y value approaching? Really, it has nothing to do with what's going on in the middle. That doesn't make any difference. I'm going to erase that here. But it's what's happening at the extremes. Unlike a vertical asymptote, which cannot be touched, it cannot be crossed, a horizontal asymptote technically can be crossed, because once again, I could have stuff in this middle section that crosses my horizontal asymptote a zillion times. It's only what's happening at the extremes. What happens as we go out this way? What happens as we go out that way? That's the concept of a horizontal asymptote. It's at the extremes. It's the end behavior. Now, there's 3 different ways to look at it. If we have, and this is just for rational functions. If we have a rational function, the leading term in the numerator and the denominator, meaning the highest power term in the numerator and denominator, is what's going to determine the horizontal asymptote. So if we take the limit as x approaches infinity of x minus 2 over x squared plus x minus 6, and you look at just the highest power terms, which are circled there, the x on the top and the x squared on the bottom are the highest power terms, well, those are the only ones that actually matter. And this is a really conceptual thing that you really kind of have to try and wrap your head around. As x gets so infinitely large, and we're talking about in the billions and trillions and much further, if I subtract 2 from that value, it basically doesn't do anything to it. 100 million billion trillion minus 2 is still almost 100 million billion trillion. It's so close to it that it's not going to make a significant difference. If I were to do exactly the same thing to the bottom, if I take 100 million billion trillion and plug it into x squared and square that number, it's huge, it's even bigger. And then I take whatever that number is and I add it and then subtract 6, it really doesn't change the number. Again, it's very conceptual. It's what happens as these numbers get so infinitely large, we can't even really fathom them. So we're only going to concentrate on the first, or the leading term on the top and the bottom. Now be sure that the leading terms are actually written in descending order. Sometimes they'll try and trick you and they'll write them out of order. Just make sure they're in the correct descending order. So really all we're looking at is the limit as x approaches infinity of x over x squared, but that simplifies because the x over x squared reduces to 1 over x. And the limit as x approaches infinity of 1 over x, approaches 0. Now, the easiest way to think about that is as the denominator grows infinitely large and the numerator stays the same, because the denominator is growing so infinitely large, I'm basically taking 1 and I'm dividing it by this absolutely astronomical number. Well, 1 divided by some incredibly huge number is 0.00000, and however many zeros we can throw out there, and then maybe a 1 at the end after a billion, trillion, zillion zeros. It's basically approaching 0. It's going to get closer and closer to 0. Won't get there, but that's what it's approaching. So that is the one that's going to be the most common, where the denominator has the higher power than the numerator. What we don't have here is if we flip those. What if we were to take the limit as x approaches infinity of something where the x squared is on the top, and maybe I've got x plus 1 in the denominator? Well, now the difference here is that the numerator is going to grow infinitely large, and the denominator isn't going to grow as fast because the power on the top is higher than the power on the bottom. In a case like this, when the power of the numerator is greater than the power of the denominator and we let x approach in infinity, it's going to go off to infinity. And that's just understanding how fractions work. If the numerator of something gets bigger while the denominator stays smaller, a bigger numerator means a bigger number overall, which is going to eventually, as again, these numbers get so incredibly large, the whole fraction is just going to tend towards infinity. It might tend towards a negative infinity. It depends on if we're approaching a positive or negative infinity. So if that actually comes up, then that's what that would be. And the last one is, if we were to have a situation, and this does come up, I might be getting ahead of myself if this is presented in another section. If we have a situation where the powers are the same, so maybe I've got 2x squared plus 2 over 3x squared minus 1. Okay, nothing we can really do to simplify any of that, but you can see that the power on the top and the bottom is the same. We still just look at the leading terms, and the asymptote here actually becomes y equals 2/3. And all you have to do, if they are the same power, is you look at the leading coefficients of the numerator and denominator and divide them. That becomes your horizontal asymptote. So ultimately what that's saying is that this graph would approach y equals 2/3 as x goes off to positive and negative infinity. Okay, so that part I did add into there. That's not in the notes. And there's one more type of asymptote that we're not going to talk about. On the next page, we do mention it. It's called a slant asymptote. It occurs when the numerator is exactly 1 power higher than the denominator, and you actually get a slanted asymptote. Not something that we're going to cover. It is covered in your book if you want to go ahead and look at it. But again, for our examples, we're not dealing with it. Okay, let's go ahead and do our example here. In example 1, we want to sketch the graph of f of x equals 8 over x squared minus 4. And as you can see from the bottom of the page, we're giving you the graph as well as the different things to fill out. So we still need to fill out all of these pieces of information. We want to find increasing, decreasing, max, mins, concavity, and vertical asymptotes. And along with concavity, if we have any inflection points, we're going to find those as well, just to make sure that we include all that. Okay, so let's go ahead and start off with, well, if we're going to find increasing and decreasing, we know we need derivatives. So I'm going to take the first derivative. And we can use the quotient rule here. We could technically use a modified chain rule if we brought the entire denominator up to the top and made it to the -1 power. I'm going to stick with the quotient rule here for simplification purposes. I think you guys will find this easier. All right, so remember the quotient rule says take the derivative of the top. Well, that's 0 times the bottom, which is x squared minus 4, minus the derivative of the bottom, which is 2x, times the top, which is 8, all divided by the denominator squared. Okay, so let's go ahead and simplify that. I've got 0 times x squared minus 4, that's 0. Then I've got minus 2x times 8, that's just negative 16x, divided by x squared minus 4 squared. That's our first derivative. In order to figure out the critical values, we need to set the derivative equal to 0 or figure out where it is undefined. So setting it equal to 0 means I'm going to take negative 16x and set that equal to 0 because a fraction equals 0 when the numerator equals 0. So if it's negative 16x equals 0, divide by negative 16, you just get x equals 0. There's a critical value. Also have to figure out where the denominator equals 0. Well, that's where the derivative is undefined. So we'll set that equal to 0. I can take the square root of both sides. The square root of 0 is still 0. Then that just means that x squared minus 4 equals 0, which means that x equals plus or minus 2. So I've got three critical values. We want to figure out increasing and decreasing. So let's create a number line. So we've got negative 2, 0, and 2. Now again, I'm going to go back to my derivative, the simplified derivative, and we're going to plug values, and we're just going to do a sign analysis here. So if I plug in a negative 3, if I plug negative 3 into the numerator, we get a positive value. If I plug anything into the denominator, think about this, if I plug any number into the denominator, no matter what I get inside the parentheses, I'm squaring it, so it becomes positive. So ultimately, if I plug a negative 3 into the numerator, I get positive over a positive, which is positive, so increasing there. Now I'm going to plug a negative 1 in. If I plug a negative 1 into the numerator, it's positive. Anything I plug into the denominator is positive, so it's also increasing there. And then at 0, excuse me, not at 0, at 1, because that's in between 0 and 2, now I'm going to get a negative on top and a positive on the bottom, so that's negative, decreasing. And then if I plug a 3 in the top, that's negative over positive, which is also negative, so decreasing. This is a really interesting function. Okay? So you can clearly tell here that there's no minimums because it never goes from down back to up, but it does go from up to down at 0. So we're going to say that we have no min, but I am going to have a maximum. So I have a maximum when x is 0. So the maximum is going to be f of 0. And if I plug 0 back into my original function right here, I'm going to get 8 divided by 0 minus 4, which is 8 divided by negative 4, which is negative 2. So I have a minimum, excuse me, a maximum value at f of 0 equals negative 2. Okay, we're going to need a second derivative. I'm going to take the second derivative from here because it's simplified. It's going to be easier to deal with. Once again, it's a quotient rule. This is going to be a little bit more lengthy. The derivative of the top is negative 16 times the bottom, x squared minus 4 squared, minus the derivative of the bottom. Now this is going to be a chain rule. It's 2 x squared minus 4 to the first power times the derivative of the inside, which is 2x. Then I still have to remember to multiply it by the top, which was negative 16x. Like I said, a little bit more lengthy. All over the denominator, x squared minus 4 squared, squared. But if I square a square, it becomes to the fourth power. All right, let's definitely try to simplify this a little bit. This is going to take a bit more algebra here. So let's see. Let's go ahead and do this in a couple of steps because I think it's too hard to walk through this whole thing. I'm going to write the x squared minus 4, however, as x squared minus 4, x squared minus 4. Hopefully you'll see why I'm going to do that in a second there. On the right side here, I can multiply the 2x, the negative 16x, and the negative 2 here all together. We're going to get plus, because I got a negative times a positive. Let's see, 2 times 16 is 32, times another 2 is 64. So we're going to get 64x squared, and then I've still got the x squared minus 4 on top from that piece. And then I've got x squared minus 4 to the fourth. Oops, that was ugly. to the fourth. Okay, so now hopefully you're going to see why I separated those x squared minus 4s. What I really have on top is I have an x squared minus 4 in each piece. I also have x squared minus 4 to the fourth power in the denominator, which means that I have 4 factors of x squared minus 4. So what I can do is I can divide x squared minus 4 out of here, and one of them out of there, which leaves me with 3 of them. That's actually going to help quite a bit in simplification here. So now we're going to get on the top, I'm going to distribute the negative 16 into here. So we're going to get negative 16x squared plus 64 plus 64x squared over x squared minus 4 cubed. And then one more simplification. I can combine the x squareds on the top. Let's see, negative 16x squared and 64x squared gives me 48 of them. 48x squared plus 64 over x squared minus 4 cubed. Okay, that's the most simplified second derivative, and that took a little bit of work to get there, but this is not uncommon with these types of functions. Okay, so from this now we can find concavity. We can also find any inflection points if they exist. Okay, so let's go ahead and set this equal to 0 or figure out where it's undefined. If I set it equal to 0, the numerator has to equal 0. Well, 48x squared, no matter what I plug in there, is going to be at least 0 or positive. Plus 64 is always going to be positive. The numerator cannot equal 0. There's no way, there's no number to plug into x to make the numerator equal 0. So it's just the denominator I have to worry about, which is going to be x squared minus 4 cubed, that's a cube, cubed, equals 0. Well, I can take the cube root of both sides and get x squared minus 4 equals 0. We're in the same position we were in the previous one. So in this case, we're going to get x equals plus or minus 2 for where the denominator equals 0. So let's go ahead and create the number line. Negative 2, positive 2. Again, I am going to look at this particular piece right here to determine the signs. So if I plug anything into the numerator, like I said, it's always positive. No, it doesn't matter what you plug in. It's always going to give you a positive value. So the denominator is actually going to determine everything. And because the outside of that parenthesis is cubed, it will actually make a difference what we plug in. So if I plug in negative 3, that's going to give me a 9 minus 4 on the inside, which is 5. Cubed is positive. So we're going to get a positive over a positive, which means it's concave up, smiley face. If I plug in something in between negative 2 and 2, like 0, again, numerator is positive. That's going to give me a negative 4 cubed in the bottom. Negative 4 cubed is negative, so now it's going to be concave down. And then if I plug in positive 3, it's going to give me a positive over a positive, which is concave up. So you might look at this, and this is again where you have to be very careful. You might look at this and say, oh, well, it does change concavity at negative 2 and positive 2. Perfect. I'm going to have inflection points. We actually are not going to have inflection points. And the reason for that is because one of the things we hadn't talked about yet is domain. Okay, we have to look at the original function. The original function, f of x equals 8 over x squared minus 4, has a domain issue. It's got vertical asymptotes. So here we're going to look at the domain. I'm running out of room here, but that's okay. Whoops. So domain of f of x equals 8 over x squared minus 4. Well, f of x can be simplified by factoring the denominator to x plus 2, x minus 2. Neither one of those things simplify, which tells me that at x equals positive 2 and negative 2, those are vertical asymptotes. And the only other thing we have to determine is if there's a horizontal asymptote. Well, remember what we look at is we look at the leading coefficients. I'm sorry, the highest power terms. The highest power term on the bottom is the x squared. highest power term on the top is just an 8. Well, x squared is clearly a higher power than a constant because x squared will grow, 8 will not. So this thing does approach 0 because the denominator has a higher power than the numerator. So y equals 0 is going to be our horizontal asymptote. Okay, we should have just about everything we need now to fill out this chart. Believe it or not, we've done all the hard work. So now we just have to fill out the chart. So increasing was from, let's see, we're going to write this. Increasing went from negative infinity to -2. And then it starts back up again at -2 to 0. Notice there I had to separate that, even though you might think, oh, it's going from increasing to increasing, so it's increasing the whole way. There's a vertical asymptote in the middle, so you can't actually include that -2. You have to stop there and then start back up again. Decreasing, same idea. So we're going to start at 0 up to +2, and then we're going to go from +2 to infinity. Okay, maximum. We do have a maximum value. It was f of 0 equals -2. The maximum is -2. We had no minimum. Concavity. This was concave up from -infinity to -2. That just doesn't look good. And then it was also concave up from 2 to infinity. And then it was concave down in between -2 and 2. Vertical asymptotes, we just decided were x equals plus and minus 2, x equals 2, x equals -2. Very important, by the way, to write your vertical asymptotes as the equation of a line. X equals, don't just write 2 and -2. Those are just numbers. It's x equals 2, x equals -2. And then the horizontal asymptote was at y equals 0. All right, let's put all this stuff together. Hopefully we'll finish this up in the next 2.5 minutes here and be under 30-minute video for one problem, really. Okay, let's plot the points that we know. We know we have a maximum at the point 0, -2. Interesting. And that's a local maximum. I know that I have vertical asymptotes. I have a vertical asymptote at x equals -2. Put a dashed line there to indicate that. A vertical asymptote at x equals 2, dashed line there. Horizontal asymptote at y equals 0, put a dashed line right there on the x-axis. Remember, what happens in between the asymptotes really doesn't matter. It's only what happens at the extremes for the horizontal. So let's see here. We have that the function is increasing from -infinity to -2. Okay, it's increasing from -infinity to -2. You can plug in various points if you want to, but the function cannot start down here and then do this. Cannot do that, because if it does, it's going through the x-axis, and we don't have any x-intercepts here. There's no way for this to happen. So that means that the function itself must go like this. It's going to approach positive infinity, and it's going to approach 0 as you go out to the left. Okay. And is it concave up in the correct places? Yes, that is definitely concave up. Okay, it says that it's still increasing, however, from -2 to 0, but it has a maximum at f of 0 equals -2. So that tells me that it's got to do this. It's got to be increasing until it hits here. And is it concave down? Yes, it is supposed to be concave down from 0 to 2. I'm sorry, in between -2 and 2, which tells me that now, because the function is supposed to decrease, it's hit its maximum and it's concave down. Now it has to come back down here. And then the last one is that it now has to be a decreasing function, but it has to be concave up. So it's actually going to mirror the other side and look like this and approach y equals 0. All right, that is plenty enough. We're just going to beat the 30-minute mark. Hopefully that made some sense. I do apologize for the length, but there you go.